Okay, so the whole purpose of this recording that I'm doing is to show you how to take a definite integral and to rewrite it as a Riemann sum. Now, it looks very complicated, but honest to gosh, since you've been doing all those left and right RAM area approximations, this is pretty easy, especially once I show you how to do it, okay? So the goal is to go from an indefinite integral to the a Riemann sum notation, and then you're also going to go backwards. And there's no MyOpen Math assignments for this. I've got that handout you can do. You get the answers. I'm going to ask you a question on the last exam. It'll be multiple choice. Actually, I might have one of each. I might have you go both ways. So let's show you how to do some of these, and then you can work on the worksheet for that practice. And you want to do that. So let me get that answer out of the way, so we don't have to look at that as I develop it. So what we've been doing this last week is we've been taking a definite integral and graphing it, and then here I probably ought to put parentheses around that, and then finding the areas of those rectangles. And we've been doing this notation out of this textbook. L sub 4 means we're going to do a left rectangle area approximation with 4 subdivisions. So what we did was we graphed it. Maybe you should stop the video and see if you can do it. Let's see. I'm going to just do a first quadrant kind of graph. So from 1, 2, 3, 4, 5, and then going up, what do I got to go to? 16, so 5, 10, 15. So obviously it's not going to be very much to scale. 1, 2, 3, 4, 5. So let's see. Let's graph that line. 1 plus 3x. So the y-intercept's 1. And then I'm going to go up 3, 1, 2, 3 over 1. And that's where I'm going to actually start this graph, right? Because that's where the subdivision is. But I guess I don't have to here. Let me just use all red. 1, 2, 3 over 1. 1, 2, 3 over 1. So where am I at? I'm at 6, 4, so I should be up at 7-ish. And I should be up at 11, 10-ish, because it's 3. It is 10. And then 4 would be 12, 13-ish. And that 5 would be up at 16. So I got this graph, I got this linear function here, right? And I want to find the area from 1 until 5. I want to evaluate that integral, and you're going to appreciate this week because then we can stop drawing these rectangles. Okay, here, let me do, I've got this, everything moving around here on me. So if we're doing an LRAM, right, we're going to do, what are we going to do? We're going to do, come from the left end, come down, left end, come down, left end, come down, and the left end, come down. Now, and one thing I'm hoping that you learned out of all that work we did was that as we go to an infinite number of rectangles, those gaps disappear, and that's the actual area, okay? And that's where we're going with the definite integral, and that's where we're going to go with fundamental theorem of calculus here next lesson. So, but now, right now, I'm trying to do the Riemann sum. Write the Riemann sum expression. So, what I've got is so I start at 1, right? So let's actually walk through this a little bit. So I know each of these is 1 wide, and one way I knew that is because I knew I want to go with 4 subdivisions. So 5 minus 1 divided by 4 is going to be 4 divided by 4. So that tells me each one of these rectangles is 1 wide. Okay, that's my dx. Okay, so you take the upper bound minus the lower bound, the upper limit of integration minus the lower limit of integration, divided by how many subintervals, that's your dx. And then that way, if you're going to infinite number of rectangles, dx goes to infinitely skinny, right? And then what we're going to do is, then we're going to find f of 1, right? Then we do f of 1, get that answer. Okay, and then we're going to do 1 times whatever that answer is times 1, right? So I don't like what I just wrote there, but you get the idea. Okay, so then what we do is we're going to add 1 to it, right? So it's 2 to get the height. To get that height, I've got to add 1 because it's 1y to my first value, which I'm starting at 1. So now it's 2. I'm going to find f of 2, multiply that by the width, right, times 1. Do that. Then I'm going to do f of 3. I'm going to take 1 and add 1 twice, right? So it's going to be 1 plus however many times I want to add in that width, right? And so I'm really getting there to be able to write the Riemann sum. And then we stop at the end, and then we add them all up, right? So we take all those areas. We do f of 1 times 1. We do f of 2 times 1, sorry. f of 3 times 1, f of 4 times 1, f of 5 times 1. And then we're going to add them all up and get the answer. So how do we do this with the Riemann sum? So we're going to get the dx. We're going to change the dx into a Riemann sum notation. So to get dx, what we do is you take, and I already said this once, so you take your upper limit of integration minus your lower limit of integration, and then we're just going to divide by generic n, because we're going to want n to get very big, right? We want to have a whole bunch of rectangles to get a good estimate. So 5 minus 1 over n is going to be 4 over n. That's our dx for any number of rectangles. And then what we're going to do, remember how we're going to take f of our starting place. Well, our starting place for this one is 1 plus, and then we're going to take however many dx's we need to add. So for the first one, we're going to add 0 because we want to start right there at 1. For the next one, we're going to add 1 of them. And for the next one, we're going to add 2 of them. So the way we denote this is take k for whatever one we want, whatever rectangle we want, times 4 over n. And then that gives us the height of our rectangle, and then we're going to multiply it by the width of the rectangle, and in this case, it's 4n. And then, of course, we're going to add all those up. So let me clear this out a little bit, and we'll do a little bit more. Okay, so we're going to add them up, and we're going to start with k equals 1. So the first one. Should we start with k equals 0? Oh, no, I don't know. We usually start with k equals 1, our first one. Okay. We usually start with k equals 1. I don't know that it would be any more wrong to start with k equals 0, but the formal thing, and I think that we can get away with that because remember we're going to let n go to infinity, right? So it'll be 4 divided by a big number is 0, basically. So I think we're okay with k equals 1. And then we're going to let it go to n, and then we're going to take the limit as n goes to infinity. There, I think that'll take care of it. Now we just got to put it in the function form. Now the function form was what? 1 plus 3n. So I'm going to say 1, not 1 because of that, but 1 because of the original function. 1 plus 3 times, and this is where I'm going to just copy. I'm just going to copy this down. I'm just going to copy this down right here, okay? So 1 plus, whoops, let me go to black. 1 plus 4k over n. Notice I did that multiplication. And then I'm going to multiply that by the width now. And then I probably need a bracket here. And then I'm going to say, I'm going to find the sum of k equals 1 to n, and then we got to say the limit as n goes to infinity. Now I think I've got that. Okay. I will say this, sometimes in some textbooks you're going to see in some notation, they'll do things like this. They'll say the limit as n goes to infinity, and they write k equals 1 to n. I mean, how they'll write this is, sometimes they'll start with, they'll go 1 plus 3x sub k. Sometimes they'll use I. Then they'll say dx. And they'll write it much simpler. They'll write it in a much simpler way. And then they'll say on 1 to 5. Or something like that. So this is a much easier process. You can almost see the function there. The only thing that makes it a little harder when they start throwing this kind of notation at you. Okay, so I'm going to ask on the exam. I'm going to ask you this. We're going for this form. Okay, but you might see it in this way in My Open Math. You won't see it in My Open Math. I can't find one like that on there. But in your next calc class, you might see that. Okay, here's another one. Now we want to write a Riemann sum. And what I want you to remember is, well, we got to find what's dx equal to. Dx, remember, is your b minus a over n. So that gives us pi over n. And then we're going to do f of the very first lower bound is 0. And then we're going to add in however many pi over n's we need, and there's no plus or minus, and then we're just going to write our times our dx, and then we're going to take the summation from k equals 1 to n, and then we're going to say the limit as n goes to infinity. And then the only thing we haven't done is we haven't written in what the function is. What's f? Let me start. You can think about that as I'm copying down this. Well, I hope you said sine of, and then we're just going to copy down that 0 plus pi k over n. What they'll do with this often is they'll write this as pi over k, pi k plus n over n, because it's 0 plus that. So if there's nothing else inside it, you know the initial value, the a is going to be 0. Okay, and then of course we need the pi n. Okay, so that's that form of a Riemann sum. I don't know that I need to do many more of these. They're all kind of the same. So the first side of that handout I'm going to make available is this. I've given you a Riemann sum. I've given you a definite integral. You could write it as a Riemann sum. So now let's do the reverse. Okay, so here's a complicated looking Riemann sum. But I'm hoping you get that same format, right? We see that says it goes an infinite number of rectangles. We start with the first one. This is that a plus, I don't know if I wrote that in the other page in this. When we go to this format, when I have f of a plus dx times dx, or k times dx times dx, that's basically what we're doing, right? And so if you have that expression written, so if we have this expression written right here, we know that number is a. And then, so then we don't know what b is. They don't tell me that, but I know that b minus a better be equal to 3, because that's what the dx is, right? So won't b be equal to 5? So we can actually get a start on this. Sorry, 2, not 3, Dan. 2 to 5. Now, what function are we trying to integrate? To me, it looks like here. Let me get some ink going. I see an e to an x and 1 plus. See how this and this is exactly the same? So that must be the x. So we're going to write e to the x over 1 plus x, and then of course we need dx. Okay, so knowing that this is A is very helpful. Knowing that this is equal to B minus whatever that A is very helpful. Remember, if there's nothing here, then it's 0. It starts at 0. Okay, so that's that definite integral. Maybe I should do one more. All right, here we go. I hope you remember. Well, once you stop and take a look at it for a minute, and then you can come back and watch. Or if you're totally lost, just try this, and when you can just watch it through. So, I guess I know that that's written A plus. Oh, you know what? I didn't put a K here. This needs to be a K. That's 1 plus the added the width of that rectangle, right? So I know that A is 1. Now I also know that B minus 1 has to be equal to 3. That tells me B has to be 4. Then I see the function that I'm taking the derivative, in the integral of is the square root of x, and then dx. And that's all. Doesn't that clean up very nicely? So that's all. So like I said, give those problems a try. I think it'll be worth your time.